Hello everyone, my name is Abhiraj Chouhan and I am a student of MTech-IT 4th semester. Today I am solving the question paper of internal 1 of numerical analysis and design for my assignment. So let's start. Question number 1. Let's begin with question number 1. We are tasked with writing algorithms to perform three operations on a polynomial px of degree n as given in the equation. The operations are evaluating the polynomial at point x, dividing the polynomial by xr, and computing its derivative. For each task, we will need to we need to compare two approaches: the brute force iterative method and recursive relation method, as shown in the table. First, let's look at the evaluating polynomial at given value x. The brute force approach computes each term independently, which means for each term we perform I multiplications to compute x to the power I, and then multiply by the coefficient a to the power I for the polynomial degree n. This result in total of 1 plus 2 multiplication which sums to n plus 1 by 2, a quadratic complexity of O n to the power 2. Here we have written a algorithm for this. Now the recursive approach uses the honors method, which rewrites the polynomial as px. This nested form requires only n multiplication and n additions, bringing the complexity down to on. For example, a polynomial like 3x to the power 3 plus 2x to the power 2 plus 5x plus 1 is evaluated at x to the power 2. Honors method computes it as 32 plus 2 to the power 5 to the power 2 plus 5 into 2 plus 1, which is much faster than computing each term separately. This method is widely used in numerical software libraries because of its efficiency and included pseudocode for both methods. Now, coming to the now now we will tackle the dividing polynomial px by x minus r, which is essentially polynomial long division. The brute force method performs the division step by step similar. How to we will do it by hand. Divide the leading term, multiply, subtract, and repeat for polynomial of degree n. This process requires n minus 1 into n to the n by 2 multiplications, again giving us complexity of O n to the power 2. Now the recursive approach, however, using synthetic division, a much more efficient technique. Synthetic division reduces the problem of n minus 1 multiplications and additions by leveraging the fact that we are dividing a linear factor x minus r. The complexity here is O n minus 1, which is linear. For instance, dividing x to the power 3 plus 2 x to the power 2 plus 3x plus 4 by x minus 1 using synthetic division involves setting up coefficients and iterative computing and new coefficient of the quotient, which is far quicker than the brute force method. This efficiency makes synthetic division the preferred method in computation algebra systems. Now coming to the next part, the derivative of the polynomial. Finally, for the derivative dp dpx by dx, the brute force method computes each term derivative independently. The derivative of ix to the power I is ix to the power I minus 1, which requires I multiplications per term to compute new efficient and summing up all the terms given us n plus 1 by 2 multiplication. So O n to the power 2 complexity by 1. This requires n multiplications for each term, resulting in O n complexity. For example, the derivative of 3x to the power 3 plus 2x to the power 2 plus 5x plus 1 is 9x to the power 2 plus 4x plus 5, computed directly by multiplying each coefficient by its exponent and reducing the power. This method is straightforward and efficiently, especially for symbolic computation tools. So this question is finished and we have written all the algorithm and even the pseudocodes for each and every operation. Moving to the next question, we are tasked with writing algorithm or flowcharts for three floating point operation, subtraction, multiplication, and division, and then completing a table to identify errors in the given computation. The table provides two sets of data for each operation, and we need to determine the final result and any errors like overflow and underflow. So let's start solving. Here we have written a general algorithm for this operation. Here we have a table and we will solve this operation and keep entering the value in the table. First coming off to the subtraction. For subtraction n minus n2, n1 minus n2, we first align the exponents of these two numbers, adjust the values accordingly, subtract the values and then normalize the result. The algorithm also checks if the results exponent exceed the maximum or minimum allowed, leading to overflow or underflow. In the table, data 1 has n1 is equals to n1 and n2 give sub n1 and n2 subtracting gives 0.0028 e minus 99. However, an exponent of minus 99 is too small for the system's range, so we will get an underflow error and the message is underflow. For data 2, n1 and n2 is equals to 0, so result is 0.2800 even, which is within range. So the final result is 0.2800 even, with no error. Coming to the multiplication, n1 into n2. For multiplication, we multiply the values of n1 and n2, add their exponents, and normalize the result. We also check for overflow and underflow in the exponent and precision loss. In the table, data 1 has n1 and n2 multiplying them, which gives us 0.4937, and the exponents is 151 plus 50 is equals to 201. So the result is 0.4937E201, but an exponent of 201 exceeds the maximum. So we will get an overflow error. With the message overflow for data to n1 and n2 giving 0.111 into 0.2234 is equal to 0.1370, and exponent 10 plus 15 is equal to 25. So 0.1370 e to 5, this also overflows, so we lose 974 in precision due to value truncation, as noted in the error column, loss of 0974. Coming for division, we divide the values n1 by n2, subtract the exponents and normalize the result, again checking for range error. In the table, data n1 has n1 and n2, so 0.998 divided by 0.1000 gives 0.998, and the exponent is 1 minus 99 is equals to 100 plus 1 is equals to 101, giving 0.9998 is 101. This causes an overflow with the message overflow for data 2. N1 is equal to 0.998 E and N2 0.1000E8. So 0.998 divided by 0.100 gives us 9.998, and the exponent is 104, giving minus 104, giving 0.9998. This underflows the message. This underflows with the message underflow. Coming to our next question, question number 3, where we will verify the associative and distributive laws of arithmetic using four Menista digits and provide the correct answer if no truncation error occurs. We are dealing with the floating point number, so finite precision can lead to discrepancies. The question provides two expressions to evaluate, one for the associative law versus one for the distributive law. Let's compute carefully considering four-digit Mantissa constraint. For the associative law, we have values of A, B, and C. First we will compute A plus B minus C. A plus B, which rounds to 0.6221 even with four digits, then 0.6221 even minus 0.5644 E. is equal to 0.0577 even. Now a plus b minus c. B minus C is equals to 0.50884 even, which rounds to 0.5088 even. A plus B minus C is equal to 0.5766 even, which rounds to 0.5766577 even with 4 digits. With 4-digit precision, both results are 0.577 even, so the associative law appears to hold. However, without truncation, A plus B minus C is 0.5766 even, while A plus B minus C is 0.5766 even as well when computed exactly, but the intermediate rounding in A plus B introduce a slight error. This correct result without truncation is 0.5766 even. This shows how floating point precision can affect arithmetic properties. For the distributive law, we have values of A, B, and C. First, A into B minus C. B minus C is equals to 4 0.40805 even, which rounds to 0.4081 even. A into B minus C is equals to 0.2267 even. Now AB minus AC, it it gives us 0.2267 even. Both result matches 0.2267 even with 4-digit precision, so the distributive law holds here and no condition is needed. This example demonstrates that distributive law is generally more robust in floating point arithmetic compared to the associative law. So let's come to our last question, true and false. Let's solve this. First, the answer of first one is true, as minimizing arithmetic operations help reduce computational error and improve performance. Second one is also true. Subtracting nearly equal numbers can cause claustrophobic cancellation, so it should be avoided or done with caution. Number third is also true. When adding or subtracting a sequence of number, starting from the smallest helps preserve precision. Fourth one is also true. Due to the rounding errors, it is dangerous to check if a floating point number is exactly zero. Fifth one is also true. Ill conditioning can arise from poor problem formulation and can often be managed by reformulation and sensitivity testing. Sixth one is also true. As numerical instability leads to error accumulation in each step, algorithm should be tested for stability. Seventh one is also true. As if rounding errors are unavoidable, using double precision is recommended to maintain accuracy. Number 8 is also true. Double precision uses more memory and may slightly slow down computations due to increased data size. Ninth one is false. The relative error of 0.013 for the Newton-Raphson method cannot be confirmed as true without exact computation. Usually needs verification with actual calculation steps. Tenth one is true. Iterative methods are evaluated based on convergence rate, computational effort per iteration, and sensitivity to initial guesses. So this conclude our this video of solving the internal one question paper. To summarize, we have explored different efficient algorithms for polynomial operations, showing how recursive methods like honors and synthetic division outperform brute force approaches. We have also analyzed floating point arithmetic, identifying common errors like overflow, underflow, and precision loss in subtraction, multiplication, and division. Finally, we verified the associative and distributive law, highlighting the impact of finite precision on arithmetic properties. Thank you so much for watching our video.